we're recording. Window.
I don't know. It was a damn great time. Stuff on the green. When you say we,
Okay, I think we're good now. It's on full screen, as big as I can get it.
Okay.
And I think we're looking good. So I'll see if we're ready to start, and then we'll get going. Okay.
Okay, sounds good.
Good. Oh, cord.
There.
Oh, I don't think we need two of these, do we? Why is it showing twice? All right, whatever.
Do we fix the sound?
We got my phone on sound.
Okay.
Can you say hello again?
Hello, can you hear me?
Yes. Yay.
All right, we're good.
You tell me when I.
Well, are we ready to go?
Yeah. I think so. Hear ye, hear ye. Can everybody sit down, please, so we can start? So we're. Hello, everybody.
Is that on?
No? Ah, thank you. Can everybody please sit down? Welcome, everybody. We'd like to start. Dr. Howarth's time is very important. We're very lucky to have him today. Thank you, Dr. Howarth.
I'm happy to be with.
I am going to have someone from the audience who's been a very active member of our 350 CT and the Sierra Club and every other organization under this earth. She's a very active environmentalist. She's a freelance journalist. Her name is Melinda Trujus, and she's with a focus on environmental climate and criminal justice issues. And for the past almost 2 years, she's been a member of Beyond Extreme Energy. This is an organization which carries out non-violent civil disobedience and other lively, artful actions at FERC, or the Federal Energy Regulatory Commission in D.C. She was arrested there in May on the bogus charge of unlawful entry, and it looks like that she and her group may be able to take their case to trial in August, which would be a great opportunity to expose FERC for its corrupt practice of rubber stamping of frack gas project permits. Let's introduce Melinda Trujus. Thank you.
So now I get to introduce Dr. Howard. Some of this may not be new to you, but some of it maybe will. Robert Howarth is a professor of ecology and evolutionary biology at Cornell University. His 1979 PhD from MIT is in oceanography, which included studying methane, so he's been at this for a long time. In 2011, he co-authored a groundbreaking report showing that horizontal hydraulic fracking for natural gas produces more greenhouse gases than coal in the first 20 years after release. This paper was cited in more than 1,500 newspapers globally, winning Howarth an honorable mention as one of the 50 people who matter in the annual Time Magazine Person of the Year for 2011. This finding was in direct contradiction to industries and governments' claims that natural gas is a bridge to a clean energy future, so it has huge implications for energy policy. He notes that global methane emissions have recently spiked due to the significant increase in fracking here in the U.S. Bob Howarth is one of a handful of researchers who are not afraid to take a political stand based on where their research leads them. He and his co-author on that controversial paper, Tony and Graffia, published an opinion piece in Nature, one of the world's top scientific publications, back in 2011 called, "Should Fracking Stop? Yes, it is too high risk." With gas explosions and leaks like the one at Aliso Canyon near Los Angeles, and leaks that exist throughout major cities such as Boston, it's becoming clear that the risk is even greater than earlier thought. Last year, Professor Howarth published a paper explaining how the U.S. Environmental Protection Agency estimate for greenhouse gas emissions may be way below what it actually is due to its undercounting of methane emissions from fracking. A few weeks ago, he briefed senior staff and scientists of the White House's Office of Science and Technology Policy in a 90-minute briefing titled Natural Gas and Methane After COP21, the meeting last December in Paris. I'm hoping he's going to share that same information with us, scary as it might be, because his perspective also offers hope for a way of dealing with the atmosphere's rapidly rising temperature. And after his presentation and the Q&A here in this meeting, we're going to be talking about the March for Clean Energy, for a Clean Energy Revolution, which has a lot to do with trying to stop fracking. And that'll be after this presentation. So welcome, Dr. Howarth.
Thank you very much for that fine introduction. Can you hear me?
Yep, we can hear you. Yeah, we can hear you.
I'm getting a bit of an echo, which is okay, but distracting to me. So let me go ahead. The presentation I want to share with you is very similar to what I gave at the White House a week ago. And I'm used to be talking to you and helping to get you to think about the march next Philadelphia, and I will be there as well. It's a very important event. Now I just need to get my computer to work. Come on. Gotta love computers. PowerPoint was working fine before, and now it's not going to, of course. Well, probably some sort of methods about trying to work on a Sunday afternoon. You frozen up. Okay, there we go. Can you see me still?
Yep,
Yes.
we're good.
Great, thank you. The context is the COP21 United Nations negotiations in Paris back in December. I was there. I was lucky enough to be one of the observer delegates. And I think it's in some ways it's a weak agreement coming out of Paris because it doesn't give a lot of specifics as to how we're going to reach a target. But the target itself is very strong. Going into the negotiations, nations of the world had agreed to greenhouse gas reductions, which would result in the warming of the planet to about 3.5 to maybe 4 degrees above the long-term pre-industrial baseline. During the negotiations, there was a push for 2 degrees almost immediately, and then for 1.5 degrees. And we'll come back and talk a minute about the importance of 1.5 and 2 degrees. In the end, what the nations of the world said is that we need to keep the Earth's temperature well below 2 degrees Celsius, again above the pre-industrial baseline. And they gave a very clear sign that they understood that anything above 1.5 is dangerous. So that's the context we're working on now. Where are we? This is a paper that was published 4 years ago in Science, and it shows the warming of the planet over the 20th century, 1900 up to 2011, rapid warming in the last 3 decades. And the green line there, labeled reference, shows what we thought the planet was doing as of 4 years ago. And we reached that 1.5 degree temperature in about 13 years from now, according to that study at the time. And in fact, we reached 2 degrees in 28 years from now. So we have an agreement to keep the planet well below 2 degrees. That means we really are talking about immediate action to slow warming. We can't wait any further. If you haven't seen this is a really striking graphic that came out last month, and I'll start it here. Ed Hawkins of the University of Reading did this. But what you're looking at is clockwise the months of the year. We're adding information on the temperature of the Earth starting back in 1850, and we're seeing each month's data here as we get closer and closer to the future. Then it's getting warmer, and in March of 2016, we had the warmest month ever, And in fact, in April 2015 and then May 2016, it's been warmer yet. We're almost at the 1.5 degree target, and it's warming faster than we realized 4 years ago. Now, why is 1.5 degrees an issue? Why do the nations of the world agree that there'd be a high risk of damage at that point? That's the message the scientific community was conveying to the political leadership in Paris. And it's basically because of worries over fundamental changes in the climate's tipping points, if you will. There are a series of expert presentations in Paris on this. The particular one I'm showing you at the moment is by Erin Pearson, who's an expert on the ice sheets of the world. And what she pointed out is one of the major ice sheets of the world in Antarctica is already melting, and that once these things start to melt, it's irreversible. So that particular ice sheet in Antarctica, even if we were to manage to slow the warming of the Earth and even cool the Earth down, that ice sheet will continue to melt. And it may take 50 to 100 years for it to melt completely, but there's no way to stop it. And as the Earth's temperature gets above 1.5 and up to 2 degrees or 2.5, then we run a very, very high risk of doing that to all of the other major ice sheets of the world, in Antarctica and Greenland, et cetera. And of course, that's catastrophic in terms of sea level rise. Again, once the melting starts, it may take half a century or more for it to play out, but there's no way to stop it. Now, to me, the more worrisome tipping point, that's bad enough, but the more worrisome tipping points have to do with changes in greenhouse gas emissions and how the Earth fundamentally relates to them. So currently, and in fact over the last century, half of carbon dioxide that the fossil fuel use is put into the atmosphere has been taken up by the world's oceans and by the world's forests and by the world's grasslands. And if that were to stop, and that uptake no longer occurs, then we are on the verge of runaway global warming because we have twice as much CO2 released from emissions. And it looks like that may actually be starting. That's what this slide shows. On the upper left are the carbon dioxide emissions from fossil fuel use globally over the last many years. And for the last 3 years, it's actually been stable. Emissions have not increased much over the last 5 years, so that's good news. However, if we look at the lower right-hand slide, that's the carbon dioxide concentration in the atmosphere from 2012. The darker line there shows the average trend over time, and the midline shows what's actually happening each year. The carbon dioxide goes up each winter, it goes down each summer due to uptake by the oceans and forests and that. And unfortunately, last year, the carbon dioxide concentration was rising at the most rapid rate it has ever risen at, despite the fact that the emissions are stable. And what that suggests is the oceans and forests are no longer performing the job they were before as effectively. And so we're getting more carbon dioxide into the atmosphere. Very scary. So again, that's a feedback from climate change, could be on the edge of runaway global warming. And of course, the reason that might be happening is precisely because of warming, which shows the temperature anomaly across the world. The temperature in April of this year compared to what it normally is in April over the last several decades. And it shouldn't come as a surprise to you that the planet was very warm in April. It's been very warm all year. And the Arctic is particularly of concern there because there's a huge amount of organic carbon tied up in the soils of those systems. And as we warm them, we increase respiration and start to put some of that into the atmosphere. You also see a cold blip there, blue, in the North Atlantic Ocean. And that's worrisome, too, because it suggests that the ocean circulation is changing. I don't have time to go into the detail, but that's what that tends to indicate. And that means that the ocean may not be able to take up carbon dioxide as they have in the past. The other feedback issue is with methane. And as we warm the Arctic, we are melting permafrost. We've lost almost 20% of the world's permafrost over the last 2 decades. And all that organic rich soil respires off with carbon dioxide, but also as methane, which is formed by bacteria, a natural process. Of course, the warming, which results in an acceleration there, is not natural at all. And then there's one other methane issue that we worry about, a form of methane that's frozen. We call it class rates. It's a water-methane mixture that's crystalline. that forms on the continental shelves of the world's oceans under pressure, and it's very temperature sensitive. So Jim Hansen, who's perhaps the world's premier climate scientist, has been telling us for some time now, looking at the geological record, that as we warm the planet to 1.8 degrees Celsius, we run a very high risk of melting methane cloud rates and pumping an incredible amount of methane into the atmosphere, which would truly be devastating if that were to happen. I want to make sure that we all understand the differences of two major greenhouse gases, and I really highlighted this in my White House briefing, and I think it's sunk in and paid attention. Carbon dioxide is the gas that most people think about, and it's a major player, and the carbon dioxide we put into the atmosphere today will be with us for hundreds, perhaps 1,000 years into the future because of the interaction with the oceans and forests. But because of those interactions as well, there are lags in the climate system. And so if we were to reduce carbon dioxide emissions now, it actually has almost no influence on the rate of global warming over the next 35 to 40 years. Methane, on the other hand, is a short-lived problem. It's in the atmosphere for 12 years or so. After that, it's oxidized to carbon dioxide, and so it's no longer a problem as methane, although it is there as carbon dioxide. But it has no long-term consequences unless the warming that results from methane in the atmosphere leads to a sort of tipping point, I've just been describing. And the other critical thing to realize about methane is that if we reduce methane emissions now, it immediately slows the rate of global warming now, very unlike carbon dioxide. So if we go back to this figure I showed you a couple of minutes ago, I referred to that reference line, the green line, and that's what happens in prediction if we were to do nothing about greenhouse gas emissions. And again, the planet's probably warming a little faster than that line indicates, but that's the general trajectory. The next line down below that that's labeled CO2 measures is what would happen if the world were to have started reducing carbon dioxide emissions in a dramatic way back in 2012. And it makes absolutely no difference in the rate of warming for the first 30 to 35 years, and then fully the planet doesn't warm quite as quickly. Two bottom lines are what would happen if we were to reduce methane emissions and also black carbon, but primarily methane is the key player here. And that immediately slows the rate of global warming. And of course, the ideal is if we reduce carbon dioxide and methane, and that buys a significant slower rate of warming, several decades of less intense warming. So that's what we clearly need to do if we're serious about the COP21 target from Paris. So I want to go on now and talk about how we compare methane and carbon dioxide as greenhouse gases, and then talk about what's going on with emissions of methane in a bit. First, let me just introduce this technical idea of global warming potential, or GWP. And it's basically the average effect of what we call radiative forcing of the greenhouse gas, methane in this case, compared to carbon dioxide over the defined period of time. So radiative forcing is the actual heating ability of the gas. So we're comparing the uptake of methane to carbon dioxide, and it is a function of time because the carbon dioxide has an influence that lasts hundreds of years, and methane's in the atmosphere for only 12 years and then it's gone. So this is from the Intergovernmental Panel on Climate Change in their most recent synthesis report from now 2.5 years ago. And what they're showing you here are the global emissions from human activity of methane and carbon dioxide compared at three different time scales. So the 10-year time scale there, the orange are the carbon dioxide emissions and the red are methane emissions compared to carbon dioxide in terms of their heating trapping ability. And at the 10-year time scale, methane emissions are actually more important than our carbon dioxide in terms of the current warming we're seeing. So methane's not a second cousin here to warming. It actually, at the shorter time scale, is more important than carbon dioxide. So if we look at 20 years, that's less so because, again, the methane is gone after the first 12 years. And if we look at 100 years, well, then it's mostly a story of carbon dioxide, and the methane's a lot less important because the methane's been gone for 88 of those years. So the longer time scale discounts the importance of methane, but of course we are concerned with what the warming of the planet is going to be over the next 10 to 20 years. That's the time frame we need to be focused on. So what are these global warming values that are in use by the scientific community? And I'm giving you here a table that shows you the 20-year numbers and the 100-year numbers. These are all from the Intergovernmental Panel on Climate Change, but from their 1996 report, the 2007 report, and the 2013 report. Basically, these numbers are the factors of increased potency of methane as a greenhouse gas compared to carbon dioxide. So in the 20-year time period, according to the most recent analysis, methane is 86 times more powerful than greenhouse gas per pound basis. The thing to notice here is that numbers are bigger on the shorter time frame, again, because methane's gone after that period and you're just discounting it. And also, the scientific community and the IPCC have been increasing these numbers steadily since we've been studying them. That's because we realized that methane has, in fact, caused more warming than we originally thought. Now, the point that I hammered home at the White House annoys me is that the Environmental Protection Agency insists on only looking at the 100-year time scale, which really discounts the shorter-term damage of methane. And up until last year, they used the value from the 1996 IPCC report, and only last year they finally updated that and went to the 2007 report. But they're still many years behind in the science. Even if they wanted to use a 100-year time period, they'd be using a number of 34. So they're discounting the importance of methane by doing that. Regarding 100 years, the EPA has been saying steadily that, well, that's what the scientific community tells them they have to do. The Intergovernmental Panel on Climate Change weighed in very specifically on that and said, no, that's not true. There's no scientific basis for using a 100-year time period. And you should use the time period, which is a concern for your question. If we're concerned about keeping the planet below 1.5 degrees Celsius, then we should be using a 10 or 20-year time period. There's no debate about that. Again, the 100-year time period greatly discounts damage from methane over shorter time periods. And I and others have been arguing for quite some time that the 10 to 20-year period is more appropriate, and the IPCC has agreed with me. Now, how much methane is that emitted in the United States? And I want to remind you that methane is a colorless, odorless gas. Smell a natural gas leak in your delivery system in your city or town, that's because it added odorizer to it. And natural gas is almost all methane, and the methane itself has the odor. Now, on the left here is a cold storage tank for natural gas, and you see nothing at all because your eye can't see methane leaks. But an infrared camera can see methane leaks because methane absorbs infrared radiation. That's why it's a greenhouse gas. And so that cloud you're seeing coming out of there is a methane leak, and these leaks are prevalent. Just a couple of headlines over the last few years. Los Angeles Times tells us that EPA has been dramatically underestimating methane emissions. I like that headline. That's actually based on one of our papers. And there's a more recent article in The Guardian, the United Kingdom, picking up on the fact that methane emissions have spiked over the last decade, and that's probably due to shale gas. Very, very good coverage. Let me give you a little bit of the science behind that that led to those headlines. And this is a little bit of a busy figure, but it's an important figure, so bear with me. What I'm comparing down the left-hand side there are various estimates of methane emissions over time, so they're going chronologically in order here. And we're looking at upstream emissions, which are leaks and venting at the site of a gas well. We're looking at downstream emissions, which are storage tanks, such as the Lethal Canyon disaster, and leaks from pipelines of various sorts. And on the right hand is full. So let's look at the upstream first. The Environmental Protection Agency came out with a number of 0.16%. That's the lifetime percentage of a gas well that leaks to the atmosphere over the time that the well is producing. There's a peer-reviewed Department of Energy study 6 years after that, in 2002, that said no, it's much more like 1.3%. I'm talking about conventional natural gas here, get the shale gas in a minute. But the EPA sort of ignored that, and right through 2010 was sticking to this number of 0.16. Tony and Grafton and I published our paper 5 years ago now, in 2011, and we said there's a lot of good evidence, more like 1.3. We pulled in new evidence beyond what was in that DOE Halo study. And the EPA responded, said yes, indeed, we were probably right, and they increased their number to even more than ours, which surprised me, but that was nice, 1.6%. They got an incredible amount of industry criticism and pressure from that, so they cut it in half in 2013, not for any particular reason, not based on any change in the science. And they were heavily criticized by the scientific community for doing that. They were heavily criticized by the EPA Inspector General for doing that. And then this year, it increased it again, but not by much. And they've made a big deal of that increase, and they're sticking with that number, but I think it's still way too low. We'll come back to that in a minute. The downstream emissions, and again, these are the pipelines and storage tanks, there are really only two numbers here. What the EPA has always been saying, they've never reassessed that, 1996, and what the Department of Energy has been saying, which I think is a better number, and that's the number we used in 2011. So the critical update here is Miller et al. Paper, which is a great paper coming out of Proceedings of the National Academy of Science, of many high-quality scientists here. They used data from over 12,000 sites across the United States, looking back at 2007 and 2008. So this is before there's any shale gas development in the United States. But they made a strong conclusion that the methane emissions from the oil and gas industry, and also from animal agriculture, are at least twice as much as what EPA had been saying in 2013. So they said that the number had to be at least 3.6%, which in fact is pretty close to what Tony and Grassi and I were arguing for conventional gas as well. Now, it's been a critical update since then, and that's last year, a fellow named Robert Howarth, who's an engineer who holds the patent on the only instrument that the EPA approves for its methane emissions estimate. Howard said that many people were misusing his instrument, miscalibrating it, and some rather heavily used studies were wrong in their methane emissions, perhaps by factors of 2 to 5, even 10-fold. And he tried hard to get that message out. He tried to work with EPA on that. He tried to work with some of the scientists who he thinks have misused it. He got stonewalled. They put out 2 papers in the peer-reviewed literature. First, just a general one, and then a specific one that directly criticized the study out of Texas. And as it turns out, the first author of the Texas study was working closely with Environmental Defense Fund. And that study has been very heavily affected by the Environmental Defense Fund. The first author is also chair of the U.S. EPA Science Advisory Board, and so he had disproportionate influence in what the EPA was thinking. Now, since these papers have come out last week, Robert Howarth, together with NC Warren, an NGO in North Carolina, has filed a whistleblower complaint against the first author of that paper and against the EPA. And my lawyer friends tell me that they think there's a reasonable chance that that could lead to criminal prosecution at that, because it was a cover of the science. This is more for humor than anything else that's related to it regarding the Texas study. This is from their website. They've now pulled it, but up until the whistleblower complaint last week, so a year or so before that, they were bragging on their website how careful their science is done, and they talk about the incredible quality control assurance and things. In addition to the instrument that measures methane, which is the thing they're probably misusing, they need to know the flow rate of gas, and that figure to the lower left is the flow reader. The reason I'm telling you this, I'll blow that up so you can see it. Someone thought it was important enough to put on this little meter to keep it upright and level. And yet, it isn't. It's floppy science. They've had very low estimates, but I think the scientific community at least now is moving on, and hopefully EPA will. I mentioned this at the White House, and the EPA staffers who were there were well aware of the problem and told me they were starting to take steps. That's progress. Okay, so let's go to shale gas now. Shale gas is a new phenomenon. It's only been around since 2005 at all, and mostly since 2009. I think the best evidence is methane emissions from shale gas are about 3-fold higher than what I've just been talking about, conventional natural gas. But the science behind this is changing really quickly because when Tony and Grassi and I published our first paper 5 years ago, it was the very first paper on the topic. No one had published anything prior to that, and the numbers we used were in fact really uncertain. So just to show you how important this shale gas, conventional natural gas production in the United States from 1980 up to 2014 is the blue line, and then some projections in the future that the U.S. Department of Energy is making. So virtually no shale gas production in 2005. Currently, it's a little more than half of all natural gas production in the United States, and it's projected to continue to grow in importance. I hope it won't, but that's the projection. In that context, I really wanted to talk about this in the White House, and I did, but I want you to think about it as well. Is natural gas a bridge fuel? The industry says it is, voted this heavily, and President Obama has said it is, and actually talked about it in 5 or 6 of his State of the Union speeches, although I was glad to see that he did not this time around, so I think he's getting better information at the moment. But the argument is that perhaps we can use natural gas to replace coal, not have to wean ourselves completely off of fossil fuels for at least a few more decades, and we can reduce greenhouse gas emissions because to get the same amount of energy, you produce less carbon dioxide from natural gas than you do from either oil or coal. And that's all true, but the problem, of course, is in the natural gas is methane, and methane is an incredibly potent greenhouse gas, so small leaks and small vents matter. And this is the paper that Tony and I, and also Renee Santoro, published 5 years ago in April, where we took that on. I won't bother with that figure at the moment. I'm going to show you an updated figure at the end, and we'll just go directly to that. Instead of spending this on. But our point was, again, that natural gas is mostly methane, small leaks therefore matter, and thought that shale gas probably emitted more methane than conventional natural gas, although we weren't really sure because the data quality was pretty poor. Now, in the lovely introduction I got, it was mentioned that Tony and I were some of the runners-up for People of the Year back in 2011. That is because of the incredible amount of press coverage that this study got. And the reason I'm telling you this isn't to brag, and certainly not to brag about being a person here. It's rather to tell you that there's also an incredible amount of pushback and a real revolution in science across the board because of publicity. And just to assure you, these are some of the other 15 runners-up in the person like something here. I'm not really not bragging about being part of it. We're just new to it and not necessarily good people. Well, one of our conclusions was that, yes, shale gas looks bad, but that the data were extremely limited and very poorly documented, and so there really was a need for better science, more measurement. And I'm very happy to say that's happened. And I'll just give you an example or two and then get into synthesizing what that means. This is typical of several recent studies. I happen to be a co-author on this, not most of the others, which is part of the reason I'm showing you, but that's typical. And what we did is to outfit an airplane with an instrument that could measure methane, in this case, measure it accurately, not one of the approved measurements, but it's better. And the airplane flew back and forth in southwestern Pennsylvania over a shale gas field. And what we're showing you here on the left is the one particular rig that's obvious on the ground, the distance the airplane is from that rig, and then flying up and down in the atmosphere. And the methane concentrations are higher, the more red and yellow, lower concentrations are blue. And then to the lower right, we just average those data that I'm showing you there on the left. And what it shows is a strong plume of methane rising from this rig. This was actually a surprise to a particular rig because the rig was still drilling, was trying to get to the Marcellus shale. It hadn't yet reached it. It had not yet hydraulically fractured. It was not in production. We would have thought that there was no methane emissions at this stage of it. That's what we had assumed in our 2011 paper. It's what the EPA still assumed because they have ignored this paper. But in fact, it's a massive amount of methane, and we found 10 drilling operations like this, all of which are emitting a large amount of methane. The other study I want to highlight is this one, a very important study published 18 months ago by German scientist Schneising, using German satellite data. And on the upper right, what you're looking at is the methane concentration across the entire forest over time from 2003 to 2012. And the axis there is defined as latitude. So the one at the top is the North Pole, 0 is the equator, and the other one is the South Pole. And what you're looking at is the concentration in the atmosphere that's averaged over that particular circumference of latitude. So there's a big increase in methane over time in the northern hemisphere. The amount of methane increase is part of the reason that the planet has been warming so quickly over the last few years, and particularly over the last year. And then when they look spatially across the circumference of the Earth, which is what you're seeing in the lower left hand, the satellite data show us that that increase is due almost entirely to an increase in methane emissions from the United States in the period 2008, 2009 to 11. And in fact, if you look in detail in the United States, it's coming mostly from the shale gas and shale oil areas. So the conclusion is that shale gas has a demonstrable effect in increasing the planetary methane burden. So here I'm showing you a summary of upstream methane emissions from shale gas and other types of unconventional gas. Again, the data here are listed chronologically from the top, so the older studies at the top and the most recent ones at the bottom. The few new ones, this is out of a review paper I published last fall, but new data are comparable. Our number at the top there is what was published in 2011 with an error bar confidence limit, a high uncertainty as to what we thought might be going on. EPA followed our lead for shale gas as well upstream, and then they cut it again in 2015, as I mentioned before. All of those light blue studies are things like the airplane flyover or other sort of regional measurements. I think they're all good studies. Highly competent scientists. I could go into reasons for some of the variations, but the two I'm highlighting there with the blue arrows are our airplane study, and then the darker blue is the satellite study, which gives a very comparable number. That orange study is the University of Texas study, which has now been thoroughly discredited, and it's low, but it's also wrong. What we now know is that the instrument failure there means that that number should be at least 5-fold higher than that, perhaps 10-fold higher than that. And I think the best estimate we have to date are the satellite data, and the reason for that is simply that they integrate in space and time. Our airplane study was a one-day study. Most of those other light blue studies are 1 to 2 day studies, and so they're capturing what's going on at a particular time, but it's not necessarily terribly representative, whereas the blue one is, and that's a lot of methane emissions. So this is a summary out of my review paper from last fall. And what I'm showing you here is the greenhouse gas footprint of shale gas compared to conventional natural gas and oil and coal. The yellowish-orange color there are the direct carbon dioxide emissions, and those are lower for a particular amount of energy from either shale gas or natural gas than from coal or oil. But the red are the methane emissions normalized to the carbon dioxide equivalency using the 20-year global warming potential. And for shale gas, methane emissions there are from those satellite data, and that black bar is our 95% confidence limit. So even at the very low end of a possible methane emission there for shale gas, the greenhouse gas footprint of shale is far bigger than coal, and perhaps much more so. One other way to look at this, and I'll be wrapping up with the science shortly, so bear with me. What I'm showing you here are the total greenhouse gas emissions from using fossil fuels in the United States from 1980 to 2010. And the bottom line there, labeled just carbon dioxide, is as it suggests the carbon dioxide emissions ignoring other greenhouse gases. And they rose in the 1990s, and they rose in the early part of this century up to 2007. And with the Great Recession, they've actually been going down steadily since then, partly due to economic recession, and partly because our society has been switching out of coal and replacing it with natural gas, shale gas, and the the carbon dioxide emissions lower. The green line just above that is what the Environmental Protection Agency says is going on for all greenhouse gases, including methane. But of course, they are underestimating methane leakage, and they are using the incredible way of discounting the importance of methane using old science and only considering the 100-year time period. So the red line is my correction for that, looking at total greenhouse gas emissions in the United States, including methane, and in this case using what I think is the best data for methane emissions and using a 20-year time period to compare with carbon dioxide. And we see that same increase up until 2007. The recession of 2007 still comes through with a reduction, but since 2008, greenhouse gas emissions in the United States have been rising at their most rapid rate ever. And that's largely because of methane emissions from shale gas. Again, that's having a noticeable consequence on methane globally and on the climate globally. So why are the emissions higher? We don't probably know. Just say that. I spent a fair amount of time talking with the White House about that, because if we don't really understand where the emissions are coming from, then it's very difficult to regulate. And of course, the Obama administration says, well, we can just regulate this and make it an acceptable fuel. I don't believe that's true. One final point on the science of methane, the even more recent satellite study that's done using a Japanese satellite data, which is less global in coverage, but has the German satellite went out of commission a few years ago, and the Japanese satellite can give us more recent estimates. So this was a study out of a group at Harvard, and what they say is that the methane emissions globally continue to rise. They're rising even more rapidly now than they were before. And again, the increase in emissions are entirely from the United States. Other countries in the world are not contributing to this. But they say shale gas is part of it. There's something else going on, too, that we don't understand. There's a major increase in methane from other sources in the United States as well. I think it may be because of leakage from pipelines and storage facilities. As we put more of the shale gas through there, we're using more gas, we're increasing the pressure to deliver it to customers, and that results in more accidents and leaks. The Lethal Canyon's case, I think, is a direct result of that. So my summary here is that the COP agreement, nations of the world tell us we want to be well below 2 degrees C, and we recognize that 1.5 degrees is dangerous. The actual targets countries of the world went into for Paris are nowhere near enough, so result in 3.5 to 4 degrees of warming. To actually reach the COP21 target, the world needs to be largely free of fossil fuels by 2050. I find that's very strong. And as a matter of equity, the United States, which has been a major contributor over time, should probably be largely fossil fuel free by 2035. And on top of that, the methane reductions are critical. We simply cannot reach the COP21 targets with carbon dioxide emissions alone. So given that, shale gas in particular has got to go. I would argue that there's still a lot of uncertainty in this, but we really should be invoking the precautionary principles this time, and is not rebuilding pipelines. It makes no sense whatsoever to be investing in infrastructure for this fuel that we simply have to get rid of as quickly as we can. Instead, whatever economic resources our nation has, I think should go into things like heat pumps and renewable energy sources and smart grids. They're not pipelines. So I want to end just with a positive note. Mark Jacobson and I and others put out this paper for the state of New York now 3 years ago, saying that with technologies that are commercially available today, the state of New York could be largely free of fossil fuel use by 2030. And we could do so in a cost-effective way that would give us better energy stability and prices, better energy security, more jobs, help address climate change, and also help with human health, because 3,000 people die prematurely each year in the state of New York from air pollution from fossil fuels. And I've taken this seriously. That's my house a few months ago in upstate New York. Our house is now carbon neutral. We used to heat with oil. We no longer do. We heat with ground source heat pumps, geothermal heat, some people would call that. And I drive an electric car. Produce our own electricity from solar. It's all cost effective. Payback period for most of these things are in the time period of 3 to 9 to 10 years of work. So they're good investments, and I'm quite pleased I've been able to do it. Finally, people tell me regularly about, okay, we need to make this energy transition. Sure, we need to get rid of fossil fuels, but it's just going to take a long time. It has to take a long time. So I've put together an example of a transition that the United States has made in the past, which did not, in fact, take a long time. And that's the transition from using horse-drawn carriages for transportation to using automobiles. And as of 1910, about 95% of personal transportation in the United States was by horse-drawn carriage. 15 years later, it was 95% by automobile. So our country has a history of being able to make changes when we want to. We need to in this case because the urgency of climate change is so real. So my final slide, I just want to acknowledge that most of my funding sources come from Cornell University, but the Park Foundation has also been very helpful to us. And the science from Park is very clear. If we're going to try and keep the planet below 1.5 degrees Celsius, we need to move away from all fossil fuels absolutely as quickly as we can. That includes coal, but particularly shale gas because of the methane emissions. So with that, I can take some questions. Let me, if I can get slides off here and you can look at me and maybe I can look at you. Thank you.
I guess we can just take hands for questions if anyone has any. Go ahead.
Diane, anyone else want to get on stack? Diane, Ben, anyone else after that? Okay, go ahead, Diane.
Hi, Dr. Howard. Thank you very much. Here in Connecticut, the legislation seems to support natural gas. There are a couple of natural gas plants, or we don't like to call them natural gas, frack gas plants, are going to be put up in Connecticut, as well as, of course, the methane, all the methane that's being supported by the legislation here in Connecticut. How do you suggest we go about stopping this yesterday?
That's a great question. You know, I'm aware of the problem in Connecticut. It's not just Connecticut. And here in New York, we've banned fracking, but we haven't banned the use of natural gas. And there are plans to build a lot of pipelines here too, and to convert coal plants to natural gas. We're fighting against it here. I was in North Carolina 2 months ago, and incredible plans for massive build of natural gas pipelines and electric plants there. So it's a real struggle. I think the politicians in most states are behind in their science. They're about 5 to 10 years behind in their understanding. They just don't understand the imperative of methane. And I think we just need to do everything we can to inform. That's what I'm trying to do. But they don't listen to science experts like me unless they're also hearing political pressure from people like you. I think we really kind of need to get in their face and get them to listen.
Go ahead, Ben.
I actually have 2 questions based on your presentation. You mentioned how we would get a lot of warming in the next 10 years based on the methane. So I was curious, is if we did pull off a miracle and shut off the development of natural or methane gas infrastructure, if there would be some kind of temperature drop, or would it is that warming like baked in once it's done, I guess is the question. The second one, you kind of answered it in a later slide, was how much of the gas produced is from shale gas, and you said it's like almost 50-50 or a little more. But is that because oil production has slowed with the rise of shale gas, and so we're not, because as far as I understand, what they call conventional gas is coming from oil drills just as a byproduct. Can you confirm that that's true, and is that why it's 50-50 as opposed to less of a percentage? So,
Let me take your first question first. If we were to cut methane emissions now, the planet would still continue to warm because of the carbon dioxide there. Even if we cut the methane emissions to 0, the planet would continue to warm over the next 35 to 40 years, but it would warm more slowly, and so we would keep the planet well below 2 degrees C, which is what we're trying to do. I think if we cut methane emissions by even, say, 30%, which sounds like a lot, but if we cut them by 30%, that's probably enough to also slow the rate of global warming to keep us well below 2 degrees C. So that's what I think we need to do. Shale gas, getting rid of shale gas is low-hanging fruit for that because, again, the methane emissions from shale gas are about 3-fold higher than they are from conventional natural gas. So bans on fracking would go a long way towards accomplishing. Your second question, shale gas is about 50%, maybe a little bit more than 50% now of all natural gas production in the United States. But your understanding of what conventional natural gas is isn't quite right. The conventional natural gas is natural gas that is migrated over geological time periods through permeable rocks in the deep underground, and they sort of get trapped under barriers which don't allow it to migrate any. The gas captured there, you can think of it sort of as a gas pocket. You simply put a well down into that, and the gas comes to the surface. Sometimes that's associated with oil, but often it's not, and it doesn't have to be associated with it. If we look at where oil is coming from now in the United States, a majority of the oil is also coming from shales, and they're also using hydraulic fracturing for that, particularly, say, in North Dakota area. And there's some methane that's coming up with that. They actually aren't particularly interested in getting it to market, so they sense and flare and burn a lot of that to keep it as peaceful on top of everything else. But that answer your question?
Yeah.
Do we have more questions? I see. Okay, so I saw in the back here, and then we'll do Melinda, this lady here, and then the gentleman in the second row. So go ahead.
Yeah, I'm just interested, really, is there a way to have access again to that PowerPoint? I was like madly taking notes, but there were like a few slides there that I'd like to be able to go back to and.
Sure. I had I sent a PDF of this. I think I might have made a change or two, but it's 99% what I just presented. So I sent to you organizers there a couple days ago. I'm happy to have them share it if they can confirm that they have it. If not, I can send it again to you.
Yeah, we do have that. We can share it.
Thank you.
Just please sign up on our mailing list if you're not already, so we have your info. Okay, Melinda?
Hi, Professor Howarth. A couple months ago, Jim Hansen spoke at Yale, and he said two things I'd like to get your feedback on. One is he's in favor of, I think he calls it, it's a carbon tax, but he calls it something else. So, there would be a tax, but it would be refunded to the people, so there would be sort of it would be neutral in terms of payments that the people would have to pay, but it would still, put a cap like on carbon. So I wanted to know what you thought about that. And the other thing is, he and some other scientists are promoting what they call a new generation of nuclear power plants. And I don't think they're not functional yet, I don't believe. But he says that there's no way we could, keep the Earth from warming way above, like what it would need to be for survival without that sort of base load that would come from nuclear. And I would love your response.
Yeah, no, those are excellent questions. Well, let me start by saying that Jim Hansen, as I mentioned, is perhaps the world's premier climate scientist, and I have the utmost respect for him. I think he's calling his carbon tax carbon fee.
Yes.
And I generally agree that such a fee or tax is a good idea, although in order to work, it's got to be a pretty hefty fee, and it really has to cover damages we're doing from using fossil fuels, which are heavy, both climate change and the public health standards. We also, if we're going to do it right, have to not just tax carbon dioxide, tax methane, need to do so in appropriate comparison. So, for the time that both gases are in the atmosphere, methane is 105-fold more potent as a greenhouse gas. I think pound for pound should be taxed as 105 times the rate for carbon dioxide. So if we do that and we make it neutral, so it's not penalizing those who can least afford, I would be in favor of that. For the nuclear power, I totally disagree with Professor Hansen. I've actually debated him on it. Let me start by saying I disagree that we need nuclear power. The plan we have in New York and Mark Jacobson for Stanford is similar to plans for the other states since then. It does not include nuclear power. It calls for using heat pumps for heating and electrification of transportation systems. Those heat pumps and electric vehicles are so much more efficient than the fossil fuel things they're replacing that, in fact, you can reduce energy use across the state of New York by 35%. Quite aside getting rid of fossil fuels, it's less energy. In terms of what need for energy, then we say we could do it largely with wind, with solar. The New York plan is actually based about 2/3 on wind. The large component of offshore wind, of course, is controversial, but we think it should be done. It's doable. The technology is there today. A little bit of hydro. We talked explicitly in our paper about nuclear. We said it was not necessary. We said that it actually has higher carbon emissions than do solar or wind because of the amount of concrete that goes into building the plants and just the incredible amount of energy that's required to build nuclear plants. Our society still has no reasonable solution to disposing of nuclear waste. I think it's irresponsible to be developing nuclear power. And of course, nuclear weapons are still a threat. And we worry about nations which might use them, and we worry about terrorists which may misuse them. And I think the best way to protect ourselves against misuse of nuclear weapons is to get rid of all nuclear, including the so-called peaceful use of nuclear power. So I firmly believe we should get rid of nuclear power.
All right, I had in the front and second row, and then we'll take you.
Okay, I have two questions. My name's Dr. Ridge. I'm from the Connecticut Agricultural Experiment Station. The first question is to do with the EPA. I feel like this agency has been in many ways harmed with potency in the last 20 years. Do you feel you can garner an ally there, or do you have an institution that is really grossly harmed in its ability to function?
Yeah, I'm saddened by what I see at EPA. I've done a lot of work with the EPA over time. I served on the Board of Science Counselors to EPA for several years. I've had a lot of close friends who work with EPA. I have friends who still work with EPA. The employees I know there are feeling discouraged. I think the agency is underfunded. I think it's under a lot of political pressure.
Yeah.
The whistleblower case on the cover-up of some of the... Once EPA and their science advisory board started to realize that there was problems with information they were using, they really had an obligation to come publicly and correct that, and they did not. They covered it up. I think that's a serious issue. I don't know how we turn this around. I mean, we have a Congress, of course, that doesn't want any environmental regulation at all. We have a Congress that doesn't respect scientific information and inquiry, and how we turn that around, I really don't know. I find it depressing, to be honest.
Yeah, I agree with you. My second question is, with this increase in energy, in all the systems around the world, how do you think this is going to affect the gyres and the currents, such as the Gulf Stream? There was a moment, didn't it shut down in 2008 for a very short period? How is that going to affect places like Northern Europe, which is dependent on these major columns of water that provide heat and stabilization in more northern climates?
Yeah, that's a great question. I'm quite concerned by changes in ocean circulation. I alluded to that figure showing the planetary temperature in last month, April actually, and that's the North Atlantic was a little unusually cold.
Yeah.
The basic planetary circulation of seawater is this big sinking of cold, very heavy ocean water in the North Atlantic. It's made up with tropical and subtropical water coming up from the South Atlantic. Gulf Stream is one manifestation of that, but not the only one. And then that cold water slowly moves down in the deep waters of the North Atlantic into the South Atlantic, off into the Indian Ocean and into the Pacific Ocean, where it eventually, on the time scale of 1,000 years or so, comes back to the surface. So it's doing two things. It's moving huge amounts of heat energy around the planet and redistributing heat, which affects the climate of Europe for sure. It actually is influencing the climate practically everywhere. Also, that cold water that's sinking is taking a lot of carbon dioxide, dissolves in it, taking it down and staying out of circulation in the atmosphere for the time period the water stays down there, which is 1,000 years. And again, that's the important protection that we've had against our use of fossil fuels so far. There's a lot of debate about whether the Gulf Stream actually stopped in 2008 or not. I'm not an expert on that. There are papers saying that it certainly slowed, that the general circulation pattern has slowed. The water is not sinking as quickly as it used to. And the reason for that, and there's pretty good evidence of the mechanism behind it, the North Atlantic is not as salty as it used to be. That northern part of the North Atlantic Ocean is still salty, but it's a little bit less salty because of the melting of the ice on Greenland and because of melting of Arctic sea ice and because of more precipitation and runoff of rivers of Siberia into the Arctic Ocean, which then flows down immediately into the North Atlantic Ocean there. And as the water becomes a little less salty, it's not as heavy as it used to be. So it's still cold, it's staying colder on the surface, but it's not sinking as fast because it's more fresh. That will certainly increase as Greenland starts to melt, if Greenland starts to melt, which it may well as we hit 2 degrees Celsius. And if we were to further change that ocean circulation, it would be very, very devastating for the world climate, as well as give us back on less carbon dioxide uptake. I find it very scary.
Yeah.
Okay, I got a question here in the second row, and then we'll go to you next.
I have a question that sort of, Professor Howarth, that sort of dovetails with her first question. It's more about strategy and discourse. What I've noticed about both the state and the National Congress is that a lot of the discourse, obviously science talked about by people who are often not conversant in science, but nonetheless it's their job to make law, not be scientists, is that they often have a two-pronged strategy. And when it comes to the science, I mean, I think it's pretty clear to us that our case is supported by clear science and more than sufficient evidence, and yet they keep banging away. I heard on AM radio yesterday they're banging away about now the moral case for fossil fuels. They're saying it's more reliable, and the technology isn't there for alternative or renewable, and that's BS. And they're denying. They're still denying climate science, which they used to do with smoking and other things. And we know that that's BS, but they're also making an economic case about jobs, and that does scare people, especially, I mean, here in Connecticut, we've had a very stagnant economy. We lost GE. We're very afraid of losing companies, and any regulation that's even slightly going to give a little prick is scaring people, and regulations are a word people don't like. So I'm wondering, for the environmental movement and just in general, would it behoove us to focus on the economic potential, or focus more perhaps on the economic potential of this energy and how it can transform the economy, how it creates jobs? Maybe we are, but for some reason that message doesn't seem to be talked about, that the memes are just not as in the open for whatever reason.
Yeah, that's another good question. The presentation I just gave, I said methane and climate change because I'm basically an earth system scientist, not an economist, and I think it's so critical to get the science right on that and for people to realize the time frame we're talking about, which is pretty short. But keep in mind, in this battle, we are up against the most powerful industry on Earth, the oil and gas industry, and they are incredibly powerful, and they're pretty effective at manipulating information and controlling information flow, and they're politicians, right? So it's one hell of a battle. We must recognize that. I do agree with you that we should and can get the message out there on jobs and economy. For our New York study, we looked explicitly at the number of jobs created, and there are a lot more jobs. And on average, when you invest money, global energy, either per dollar or per energy is produced, you get for 3 to 4 times more jobs out of the permanent jobs than if you invest in fossil fuels. For the New York plan, and it's true in Connecticut as well, the case is stronger even because the jobs that are supporting the fossil fuels that we consume in the Northeast are not local jobs. They're coming from Texas, maybe Pennsylvania, at this point, maybe North Dakota. They're not in Connecticut, they're not in New York. So for the U.S. as a whole, we get 4 times more jobs by going the renewable route. It's more like 10 times more for Connecticut or for New York. So the jobs cases are really clear. I think the economic is clear as well. At the moment, that's absurdly cheap. No way anything can compete with it simply on the basic price if you ignore the human health costs and the climate change costs. That can't last. The price will go up, and it's going to oscillate. It's going to be uncertain, and to cause a lot of economic harm as bounces back and forth. It's about $2 per million BTUs today, but it was 13 just a couple of years ago, and it's going to be 5 to 6 in another few years, and maybe back up to 12 again. And at that point, you don't want to be basing your economy on it. So I think the economics are there. There's some really good economic analysis that we could do a better job of getting out to people. I agree with you.
Okay, I got the woman in the middle, and then take Stan next.
Hi, I wanted to know what's the production, if you will, of the methane in the United States in percentage compared to the rest of the world? And then my second question was, I didn't really understand, or maybe, can you explain the graph again with the production of methane that started to dramatically rise after 2005? Does that mean that now we have substantially more than prior to this administration?
Yeah, so let me start with the second part there. Methane emissions started to increase dramatically for 2008 or 2009, according to the satellite data. It continued to increase then, according to the more recent satellite paper as well. That's a U.S. phenomenon. Methane emissions in the rest of the world have not been increasing over that time. They've been steady. So it's only in the U.S. that they've been increasing, and at least half of that is because of shale gas, maybe almost all, but we don't really know because it's still recent science, and there are only so many of us working on it. But yes, the Obama administration has presided over a huge increase in methane emissions, and it's globally important. What's the first part of your question?
It was a separate question. I wanted to know what's the, so sometimes they say the U.S. produces a certain percentage compared to the rest of the world. I was wondering about methane.
Yeah, the United States is producing about, or emitting almost 40% of global methane emissions at this point in time. And the number one source of that is the oil and gas industry. Number two source, the animal agriculture, which produces a lot of methane. And those methane emissions, too, could be reduced, and we should be working on that as well. We're a big part of the problem.
Stan?
I would dispute this carbon fee idea that Professor Hansen has. I mean, the tax part makes a lot of sense, and your addition, taxing methane much more than carbon dioxide, is a great addition. But the idea that we just take the money and give it back is, I think, a wild experiment, a free market bubble. We need those hundreds of billions to completely change the economy, to go to 100% renewable in 20 years or 30 years, whatever you were saying. And I think it's a bad idea to put people off on that radical, untested notion that just people will just spend wisely. I mean, we know we have to plan something out, and we have to do it very soon.
Well, I don't disagree with you. I'm not a big fan of free markets being able to solve things on their own. I mean, what I meant to say, I'm not familiar with exactly what Jim Hansen said when he was giving the lecture there in Connecticut, but he's made the case a couple of different ways. What I do agree with is that at least part of those funds should go back to the less economically fortunate in our society, not just to do whatever, but to help with the energy transformation, to help them weatherize their homes, help them get natural gas furnaces out of their home and replace those with on-source heat pumps, installing PV, things like that. So I do agree that the funding should go to the energy transition. I think that a reasonable share of it should be earmarked towards the less economically fortunate, who in some ways would be the ones most hurt by the other one.
Is there any way we could do a final round of questions? I think we're getting close to the end of time. Okay, we'll take you. Anyone else? Okay, go ahead, sir.
Yes, thanks for your presentation, Professor Howard. You put a lot of burden on shale gas as the source of increased emissions. And that really doesn't stack up with my experience in Marcellus. I would say that the technical engineering, which is mainly American-based, and the instrumentation, whether it's measurement, safety, control, communications, is state-of-the-art in Marcellus. And that's both upstream and midstream, and in the processing of the gas, because a substantial proportion has to be processed. And I just don't understand why there should be such a high level of emissions given the effort to bring technical solutions to shale gas.
Okay, let me, the evidence I'm using for the high emissions are integrated measures. So it's the satellite data showing spatially over time that methane has increased and where they've increased. It's clearly tied to the shale gas areas where there are satellites showing these emissions. As the details, I actually put the slide there saying that we don't know in detail where it's coming from. But let me give you a couple of examples. First on the midstream, on the storage. We're storing more gas than ever because we're using more gas than ever. The use of gas is highly seasonal because most gas is actually used in the United States for heating, so we produce it year-round, but we're using it mostly in the winter, and so we need a large storage capacity that's going to work. And where are we storing the gas? Well, you know, the Aliso Canyon case, which went on leaking until it was pretty much depleted, went on for, 3.5 months or something this past winter. That's typical of the way we store natural gas. In this case, it was once an oil field. The oil was pumped out. There's space, if you will, underground there. It was converted into natural gas storage facility in the 1980s. They took off the blood detectors over time. Why? They were required by regulation. They were actually cited 3 different times over a period of a decade or so for not meeting the regulations, but nothing happened. They continued to ignore it. I believe they did increase the pressure in that facility because of the increased use of natural gas, and it led to this disaster which they couldn't control because there was no blowout protector. So, you know, that is not state-of-the-art technology, and yet I think it's quite typical. You look at the pipeline transmission, either long-distance high-pressure pipelines in the United States or the urban lower-pressure distribution pipelines, more than half of each of those in the United States are more than 50 years old. High percentage of the pipelines in New York City are cast iron pipes that are flooded end to end that are 100 years old, and they leak like a sieve. Not state-of-the-art technology. In terms of the actual shale gas development, early on, the industry was clearly venting a lot of gas at the time after they hydraulically fractured. They pumped down, to 5 million gallons of water and some chemical additives, and then that flows back to the surface a few days to maybe a few weeks, something like that. And back in 2009, 10, 11, 12, massive amounts of methane were coming back up to that water, and they were simply venting it to the atmosphere until they could get the water out of the way and start putting a pipeline. There was technology available. They didn't have to do that, but that was the cheapest, easiest thing for them to do, and so that's what they did. That's now against the law, although there's tons of exceptions, and I'm not just being enforced very well. And then, again, just to remind you of what I said, our airplane flyover study, we found these 10 wells which are highly emitting. We don't really know what was going on there, but they had not yet reached the shale, so the methane is coming from something else. And what we think was going on, this is an area, southwestern Pennsylvania, that saw oil and gas development 100 years ago. Coal mining has been going on there for 130 years, 140 years. They're drilling through all of this past industrial activity, and we think they're hitting little pockets of gas from previous wells and from coal mines as well, probably, that have migrated from the gas wells. So, you know, that's not being regulated. Industry doesn't seem particularly concerned about it. So I just don't accept that this is really state-of-the-art technology.
I just want to thank you, Dr. Howarth, for taking the time to, do this presentation for us today. We really appreciate it. And, we hope to continue learning more stuff from your research.
Thank Eric Stam, who at the last minute came with a great sound system.
Thanks a lot, Doctor.
Take care.
Thank you.